Okay, so jumping right in. Potential energy diagrams. We're really going to get into this later on in the year, but for right now, all you need to know is that a kind of graph that looks like this, where you have a flat line here, it reaches up and then it flatlines higher than when you started, indicates endothermic because there's more heat in the system after the reaction. So this is the amount of heat we had to start. This is the amount of heat we had at the end. Notice it's higher. Now I know there's no units on the axes, but this would usually be energy in kilojoules. Noticing that we are higher here than here. Now exothermic, you would end lower than where you started. So this is our start. This is our end. So there's less heat in the system afterwards. We're going to really get into this later on, but for right now, that's all you need to know. Heat capacity, the amount of heat needed to increase the temperature by an object 1 degree Celsius. This depends on mass and composition. However, this is what we're really going to need, specific heat. Specific heat is represented by the variable capital C. Don't confuse it with carbon or degrees Celsius. Specific heat is the amount of heat needed to increase the temperature of 1 gram, so the mass is definite this time, and the temperature change is definite. The only thing that changes is the composition. The units are joules divided by grams times degrees Celsius. On the reference table, you would also see joules over grams times Kelvin. But in either case, you have joules divided by a mass times the temperature. This is what we're usually going to use just because we measure in degrees Celsius. Now, if I wanted to actually figure out, okay, I know I have an exothermic reaction, I can feel the heat given off, I just want to be quantitative, I would use this formula. Q equals MC delta T. This is on table T of the reference tables under heat. So if you're looking on table T, you can see what Q, M, C, and delta T all stand for. Q is a heat transfer, usually in joules. M is a mass, usually in grams. Our C is specific heat, usually in joules per grams degrees Celsius. And our temperature change in this case would be degrees Celsius. So let's say, for example, if our temperature or if our specific heat was in Kelvin, then this would also have to be in Kelvin. You just need those consistent units. If you do your calculations and you find that negative Q is your answer, a negative value, this is exothermic. If you find that after you do all these calculations you have a positive Q, that is an endothermic reaction. So we can tell just from our math whether we absorbed or lost heat. So delta T means a change. So remember, how do we calculate a change? When we're calculating the slope of a line, it would be change in y over change in x, which is y2 minus y1, our final y minus our initial y. So that exactly is what we're doing here. Delta T is final temperature minus initial. T final minus T initial. If delta T is positive, that means we absorbed heat. So for example, if you had we ended at 50 degrees Celsius and we started at 25, your delta T would be 25 degrees Celsius, and seeing as that's positive, it was endothermic, which makes sense because you started at 25 and you got to 50, you must have taken heat in. If delta T is negative, that means the reaction is exothermic. So let's say we ended at 50, but we started at 60, final temperature change would be negative, which means, yeah, we were at 60, we became 50, we must have given heat off. Okay, let's do a couple calculations. We're going to be using the formula Q equals MC delta T. Let's go back for a second. Wish there was a faster way to do this. Maybe. Specific heat values. If this is water, you want to look on table B. So if you go to the reference table and you go to table B, it says the specific heat capacity of water is 4.18 joules per grams times Kelvin, which we will usually use degrees Celsius just because we're measuring in Celsius. But water, that is provided to you. If it's others, it'll have to be given in the question. However, if it's water, they might ask you to look that one up because it's on the reference table. Oh, yeah. All right, moving on. Okay. Calculate the heat release when 100 grams of water is cooled from 25 degrees Celsius to 10. So we're calculating heat. Heat is Q. Here's our mass. It's water, which means our specific heat is 4.18 joules per grams times degrees Celsius. Here's our two temperatures. Delta T equals T final minus T initial. So final minus initial. There it is. So when you do this, you get a negative value. And so we are not going to use that middle number for sig figs. And technically this should be 10.0 and this should be 25.0 and this should be 100 point or something. Because it looks like I rounded to 3 sig figs. Anyways, regardless of sig figs, notice this is a negative value. So negative value means it's exothermic. Another way to tell if you did it right is look, heat is released. That word was mentioned. Our temperature went down. So the math should back up the word problem and vice versa. And you just multiply those three things together. Calculate the change in temperature. So change in temperature is delta T when 50 grams of iron produces 10 joules of heat. And I'm sure I've got something like this going on for sig figs. Now, notice I'm not dealing with water. I'm dealing with iron. So since it's this iron, I had to be provided the specific heat value. So I'm looking for delta T. So let's add that in. Our Q, our mass, specific heat, and that's what we're looking for. So you're going to multiply the 50 times the 0.46, divide both sides by that value, and you get 0.43 degrees Celsius. Okay? Calculate the mass of mercury needed to release 50 joules of heat after a 30-degree decrease in temperature. Notice that mercury's specific heat was provided since it's not something that I know. If it was water, remember table B. So I'm looking for mass. So here's my Q. 0.0 probably. Mass is what we're looking for. There's that. And all right, we know our degrees. There's that. So we're going to divide both sides by that quantity. Of course, I have this, so I can't help myself. Oh, look, negative here. I forgot. It's a given off. So given off the 30, given off the release. Release means negative Q. And so those two negatives cancel out. Now, let's say you forgot your two negatives, or maybe you put one negative in and not the other. If you got a negative mass, you screwed up something. So actually, in this case, it doesn't really matter, but you should include negatives if necessary for like a release, a negative Q meaning exothermic. Calculate the final temperature of 100 grams of water at 20 degrees Celsius absorbed 1392 joules of heat. Now, normally we have Q equals MC delta T, but that's not going to be what we're looking for. We're looking for a final temperature. And so what we do is we need to substitute in the definition for delta T. So we would have Q equals MC, the quantity, T final minus T initial. Now that I put that definition of delta T in, can't you see now that we can solve for the final temperature? So see what I did. Here's my Q. Here's my mass. Water specific heat was not provided to me, but I know that since it's water, it's on reference table B. I'm looking for T final. So what I would do first is I would multiply 100 times 4.18. That looks a little crazy. Yeah, so here's those two things multiplied, and then you would just get, you know what, I'm going to go back. I'm going to leave it here because I think that looks confusing. So now, let me grab my calculator. All right, so I have 4.18 times 100, which I shouldn't have needed a calculator for, but I did. 418 times the quantity TF minus 20, which really should have that, the 1392. Okay, now divide both sides by 418. Don't distribute you 418 because you only have to take it out anyways. So 1392 divided by 418 gives me 330, a whole bunch of decimal places, which I don't need. TF minus 20. All right, how do I get TF by itself? I'm going to add 20 to both sides. 20. And you get, now let's talk sig figs. We've got 4 here. Technically, this should have 4. Don't count that. And this should have 3. So let's go to 3 sig figs. 23.3, and that would be degrees Celsius. So the text I had already was just kind of messy, but you still get the same answer. All right, if you have questions, please reach out, let me know. Thank you.